Now we're going to start the second set in our text, and this is called a passport to advanced mathematics. So far we have learned only one type of function, and that's a linear function. So I actually have one written down here, which go ahead and write that down. F of x equals 30 plus 2x. This is a linear function. Okay, so in the last half of the Heart of Algebra, we examine linear functions in full detail. In this section, we're going to look at exponential functions, quadratic functions, polynomial functions, and rational functions in detail. Okay, so before we get into exponential functions, I just want to do a quick review on linear functions and what they look like. Okay, so f of x equals 30 plus 2x. This is a linear function. It makes it linear because you just have this x value is not raised to the 2 or 3. You don't see x squared, x cubed. It's also not under a square root. It's also not in a denominator. This would be a linear function. We have that the slope m is the number attached to the x value or whatever the input is, and b is 30. Okay, so remember graphing this, we would have the point 0, 30 here. Okay, let's just go ahead and do an x, y chart, or x, f of x. I always like to use f of x here. Okay, I'm just going to start at 0 and we'll go up. Okay, so if we plug in 0, okay, that's 30 plus 2 times 0. That would be 30. Okay, which we knew that's what it was going to be because of our y-intercept. Okay, if we plug in 1, that's going to be 30 plus 2 times 1, or 32. If we plug in 2, that's going to be 30 plus 2 times 2, which would be 34. If we plug in 3, it would be 36. Let's do one more. Plug in 4, it would be 38. Okay, we could keep going here. Okay, so let's just look at these output values. You have 30, 32, 34, 36, 38. Okay, so to get to the next value, you add 2. Next value, add 2. Next value, add 2. Okay, so we would continue that. Okay, this is always true for linear functions. You're adding here, adding, adding. You add the slope to get to the next consecutive x value. Okay, so add 2, add 2, add 2. Okay, so now let's go ahead and look at exponential functions. It says, suppose a person becomes infected with 30 bacteria from a sneeze in a crowded room. If each bacteria splits into 2 bacteria every hour, okay, so that means that 30, each one of those 30 is going to split into 2, then the population doubles every hour. Find the number of bacteria at each hour by filling in a table, and then we're going to create a function for the situation. Okay, so let's just say x is our input, and that is going to be at each hour. So I'm going to put hour here. And then our output, let's use capital N of x for the number of bacteria. I'm going to make this a little shorter. We don't really need all that. Okay, so at hour 0, so that's when we're starting the time for this bacteria, there are 30. Okay, at hour 1, okay, so 1 hour passes. How many do we have? So it says each bacteria splits into 2 every hour, then the population doubles. Okay, so that means each of these 30 bacteria splits into 2. So this population is going to double, so we'll have 60. Okay, and in our heads we did 30 times 2. Okay, after 2 hours, again, this population is doubling. Okay, so in our heads we did 60 times 2. Or you could write 30 times 2 times 2. Right, because that's 30 times 2 and then you're doubling again. Okay, third hour, we're going to double this again. So this would be 240. So again, that's 30 times 2 times 2 times 2. Let's do one more. After 4 hours, we would have 480 here, which would be 30 times 2 times 2 times 2 times 2. Okay, so what's happening here? Okay, so first of all, notice to get from 30 to 60, we multiplied by 2. From 60 to 120, we multiplied by 2. So we continued that. Okay, this is always true for exponential functions. Okay, to get to the next consecutive output, we multiply by something. Okay, so remember linear, you add. Exponential, you're multiplying. Or you could be dividing. Okay, so linear, if our slope was negative, we would have been subtracting. If we have, we'll look at this here, but sometimes you're dividing. Okay. Okay, so exponential, multiplying, dividing, linear, adding, subtracting to get to the next consecutive output. Okay, so all we need to do now is write out our function n of x. Okay, and I'm going to use these values here. Okay, so we're just looking down here. What doesn't change, that would be 30. 30 doesn't change. Also notice the 2's aren't changing, so we're always going to have a 2. Okay, but what is changing is how many 2's we have. So here we have 1 2, here we have 2 2's, here 3, here 4. Okay, so notice that the x value determines how many 2's we have. So we're going to be using an exponent here. Okay, so this is what an exponential function looks like. We have n of x equals 30 times 2 to the x. Okay, so let's go ahead and go into the definition. It says exponential growth, okay, notice it says growth, is modeled by a function of the form f of x equals c times a to the x, where a is greater than 1. The base a is called the growth factor, the factor by which f of x is multiplied by when x increases by one time period. The constant c is the initial value, that's where the value in x equals 0. So it says for the above situation, what is a and what is c? Okay, so again, a is called the growth factor. That is what the function is multiplied by each time, okay, which we can see here is 2. Also comparing it to this form, so I'm going to just put over here f of x equals c a to the x, and we had n of x equals 30 times 2 to the x. So you guys can see here what a is. A is 2, okay, that's what we multiplied each time by. And then c is the initial value, or the value when x is 0, which you guys can see is 30 here. Okay, so c is the initial value, a is what it's being multiplied, and then later we're going to look at what it could be divided by. Okay, the graph of exponential, this is for growth only, has general shape below. Okay, so exponential growth looks like this. So you have a curve now. Okay, so this is a different type. Okay, this point here is 0c, and then we have a horizontal asymptote on the x-axis. Okay, what asymptote means is this curve gets really, really close to 0, but it's never going to actually cross it. So you might have a value of 0.0000001. Okay, that's really, really close to 0, but it's not actually 0. Okay, on to page 2, we're going to do some examples. So top of page 2, it says find models for the following exponential growth situations. Okay, number 1, a bacteria starts with 15 bacteria and triples every hour. Okay, so we want our function to look like ca to the x. Okay, because it's tripling, we know we're going to be multiplying. So we need to pick out our c, and we need to pick out the a. Okay, so c is where or what the population starts with, or the value that where x is 0 here. Okay, so c, it says a bacteria starts with 15 bacteria. That means c would be 15. And then it's tripling every hour, so the number that represents tripling is 3. So you're going to be multiplying by 3 each time. So our function would be 15 times 3 to the x. Okay, number 2. A rabbit farm started with 100 rabbits, and each year the first population is multiplied by a factor of 2.5. Okay, so again we need to find c. That's how many rabbits we'd start with. Looks like we started with 100. And then a is our growth factor, and it tells you exactly you're going to multiply by a factor of 2.5 each year. So that's our a. So our function, which I'm going to change the name to g, is 100 times 2.5 to the x. Okay, sometimes the growth factor is not given to us directly. Okay, so sometimes we don't have it's tripling every hour, or it's multiplied by this. So we use the formula growth factor, that's a, equals population after x plus 1 time periods divided by the population after x time periods. Okay, so that just tells you, I'm just looking down here, 2 consecutive ones. We would find a by doing like 12 divided by 4 or 324 divided by 108. So using 2 consecutive outputs. Okay, you can divide, because to get from 4 to 12 we multiply, or 12 to 36 we're multiplying. Okay, so that's how we would find our growth factor. Okay, so let's go ahead and look at this example. It says the table below represents the population of a certain bacteria each hour. Find the 1 hour growth factor and find a model for the population. What will the population be in 24 hours? Okay, so we have to do a couple things here. We need to find C, and then we're going to find A, then we'll have a model, and then we're going to find the population in 24 hours. Okay, so C is the population at the very beginning, or when x equals 0, which you guys can see that is 4. Okay, A is what you're multiplying the output by each time. So to get from 4 to 12, we multiply by 3. To get from 12 to 36, we multiply by 3. We'll just check this. This is multiplied by 3. This is multiplied by 3. So that's what our A is, okay? You could do it like that, or this definition tells you that A is going to be, take 2 consecutive. So I'll just do 36 divided by 12, and you get 3. Okay, you could have chose 12 divided by 4, 108 divided by 36, as long as they're consecutive. Okay, so then our function is 4 times 3 to the x. So there's our model. And we want to know how much this is bacteria we'll have in 24 hours. So that's going to be f of 24. Okay, so that is 4 times 3 to the 24th. Okay, so I'm going to show you how to put this in your calculator. This should be a review. Clean off that screen. Okay, so we'll do 3 to the 24th first, which is going to be a huge number. That's 3 times 3 times 3 times 3, 24 times. Okay, remember that this E11 means times 10 to the 11th. Okay, so that's a huge number. So that means take this decimal point, move this over 11 times. So you're going to have a ton of zeros after this too. Now we have to multiply by, it was 4. Okay, so I'm just going to put equal, actually I'm going to do approximately here. Let's do 13 times 10 to the 12th. Okay, so take this decimal and move it over 12 times. Okay, so that is a lot of bacteria. Okay, next example, a rabbit farm starts with 100 rabbits, and after 5 years there are 612 rabbits. Assume that the number of rabbits grows exponentially. Find a model for the situation. Okay, so let's go ahead and write our information down that we have as a chart. So let's do x4, this is number of years, and then it was, let's just do population here. Okay, and let's just call this f of x, which I should have wrote that opposite. Okay, so it says a rabbit farm starts with 100 rabbits. So at time 0 you have 100. And then after 5 years, there are 612 rabbits. So we have 5 years, there's 612. Okay, find a model for the situation. So we don't have 0 to 1, 1 to 2, okay, but we do have 0 to 5. Okay, so we can go ahead and find this factor. Okay, so times something. So A would be 612 divided by 100. Okay. And what we need to do there is, which is 6.12. Okay, instead of just leaving it like that, we're going to go ahead and put 5 years here. I'm going to put 5-year factor. Okay, so don't be confused with this being the 1-year factor, okay, because from 0 to 1 year, you don't multiply by 6.12. That's 0 to 5 years, okay? So for this function here, we can only go up by every 5 years. So we could see in 10 years, we would multiply by 6.12. And then we could do 15 years, and then 20, and then 25. We can only go up by a factor of 5 here. Okay, so we couldn't figure out how many rabbits we would have in 8 years, because it's not a factor of 5. Okay, so we need to finish this. So C is 100. Okay, so our population, rabbit population, would be 100 times 6.12 to the x. And I'm going to again put in parentheses just because we need to keep this clear. This is for 5. It would only go
up by 5 years. So if I said what would the population being 10 years, you would have a 2 here. In 15 years, you would have a 3 here. So that's a little confusing, but you might see something like that on the SAT. Okay, page 3 says very top. The growth rate of a population is the proportion of the population by which it increases during one time period. Okay, so this is different from the growth factor. It's a proportion. I'm going to put here normally a percent. Okay, so proportion could be a fraction, a decimal. In this case, an exponential growth or decay case, it's normally a percent. Okay, so growth rate is exactly a minus 1, and a equals 1 plus r. These are the same formulas. I memorized this one. Okay, so this is something you'll want to memorize. Okay, a equals 1 plus r. Okay, so that means if we have the growth factor, we can get the growth rate. If we have the growth rate, we can get the growth factor. Okay, also notice that r is greater than 0 because it's growth. Okay, so let's do an example of why this is important. It says a certain bacteria grows at a rate of 20% each hour. Number 1, find a function p that models the bacteria population after x hours if there are 63 bacteria to start. Okay, so let's go ahead and write out what we need. We need c, which is 63, that's where we started. We also need a, okay, which we don't have. So it doesn't say the bacteria was multiplied by a factor of this each, this was hour, or it is tripled every hour, something like that. We're not given that, okay? But we are given r, okay? We're given a rate here, which is 20%. So it says it grows at a rate of 20%. Okay, so the rate is 20%, so that is 0.2. Okay, so going back up to this formula, a is 1 plus r. Okay, so that would be 1 plus 0.2, which is 1.2. Okay, and we have everything we need. It says to call this p. So p of x would be 63 times 1.2 to the x. Okay, number 2, how much bacteria is there after 8 hours? Okay, so we want to do p of 8. So that's 63 times 1.2 to the 8th. Okay, remember your order of operations, you always want to do exponents first. So 1.2 to the 8th times 63, I think. Let me check that. Yeah. Okay, so it's about 270.89, and this was bacteria. Okay. All right, so make sure you have this memorized, this a equals 1 plus r, because you'll probably see one like that on the SAT. Okay, bottom of page 3. It says exponential decay is modeled by a function of the form f of x equals c a to the x, where a is in between 0 and 1. Okay, so exponential decay is not any different than this f of x equals c a to the x, except a is in between 0 and 1. Okay, so if you have growth, exponential growth, a is greater than 0. I'm sorry, a is greater than 1. Okay, if it's decay, a is in between 0 and 1. The decay factor a, where a is a positive number, is less than 1. Notice here next, the decay rate r that still satisfies this is always negative. Okay, so if you know you have decay, the rate will be negative. Okay, so bottom of page 3, let's do an example of decay. Oh, I need to tell you the picture of decay too. Decay looks like this. So here's exponential decay. Again, it's very similar to growth. This point is 0c, okay, and then this here is another asymptote on the x-axis. Okay, bottom of page 3, it says a patient is administered 500 milligrams of a pain reliever. It is known that 50% of the drug is expelled from the body each hour. So there we have decay. Expelled means it's leaving the body. What amount of the drug will remain in the patient's body after 6 hours? Okay, so we need a couple things here. We need C. That is 500. That's where it started. We also need A, which we're not given. Okay, but we are given R. Okay, it says 15% of the drug is expelled each hour. Okay, so that's 15%. Okay, but it's expelled, so it's actually negative. Okay, so negative 0.15. Okay, then A is 1 plus R. Okay, so that would be positive 0.85. Okay, so now we have decay. Notice the A is in between 0 and 1, so we have decay. Okay, so our function would be C, which is 500, times 0.85 to the x, where x represents hours. Then we want to know how much of the drug is in the body after 6 hours, so F of 6. So that is 500 times 0.85 to the 6th. I got about 188.57, and this was in milligrams. Okay, so there's a good example of exponential decay. If we were to graph this function, okay, it would look like this. We would know this point is 0, 500. So this point is 0, 500. Okay, page 4, exponential regression. Okay, this is only if you have a graphing calculator. So again, this would be nice to have for the SAT. You are going to be given some scatter plots for the exam. You're also going to be given tables, and you'll have to find your regression, your exponential curve. Okay, so I'm just going to read through this. I'm going to quickly go through this. If you don't have a graphing calculator, go ahead and skip through this part. If you do have a graphing calculator, follow along with me. I'm going to be moving pretty fast, okay, because we've already done regression, and it's almost exactly the same, okay? But do try this in your calculator. Okay, so it says, when given a data set, first make a scatter plot of your points. If it looks like growth or decay, the model for the data could be linear or exponential. Do regressions for both, making sure to write down the correlation coefficient for both regressions. Okay, you can go ahead and cross out this. The correlation coefficient is not on the SAT, so you don't need to know that. Okay, it says, given the table of data below, decide whether the decay is linear or exponential. Then find a function that models the data. Use the model to predict y for x equals 60. Okay, so to do regressions, remember we go to stat, over to edit, and we need to put all of our information, stat, just press edit, not calculate. We need to put all of our information into our list. Okay, so I'm going to go ahead and clear. And then I'm going to put my information in. So L1 is going to be X. Okay, and then L2 is Y. Okay, I'm going to check those values. 0, 8, 16, 20. Okay. Now let's go ahead and turn on our scatter plot, and we'll just look and see what this looks like. Change the window 0 to 50 for X, 0 to 5. Go ahead and clear out all of your... Okay, so here's what the scatter plot looks like. Okay, you have decay here. Okay, we were decreasing. It could be linear, it could be exponential. I'm just going to tell you that this one is actually exponential. Okay, like I said, you don't need to know correlation coefficient, so I'm not going to go over why. But we're going to do this exactly like how we do linear regressions. Okay, so go to stat, over to calculate. When you did linear regression, you chose number 4. Now we're looking for exponential regression, which is number 10 on mine. Okay, if you have my version or newer, your page is going to look like this. If you have an older version, it's going to say exponential regression. I believe it has open parentheses. You want to type in L1, comma L2, as long as your list, as long as your X and Y is in that. Okay, here's the comma button, which I should have showed you. So open, close parentheses, and comma. L1 is second 1, L2 is second 2. Okay, so if you have my version, you just need to enter through here. Okay, so it says y equals a times b to the x. A is approximately 4.79. B is approximately 0.9964, which I made a couple more decimal places here because I didn't want to round to 1. Okay, be careful with this one. A in this example is the initial value. Okay, so the calculator doesn't align exactly. Okay, so f of x is going to be 4.79 times 0.9964 to the x. So there's our function. And we want to estimate the output when x equals 60. So we're going to do f of 60 here. So it'll be 4.79 times 0.9964 to the 60th. 0.9964 to the 60th times 4.79. I got about 3.85. Okay, which makes sense. You are decreasing here, so by the time you get to 60, you should be under 4. Okay, and then we just have about half a page left for solving exponential equations. Okay, so we know how to solve linear equations. We've done that. So a linear equation would look something like this, something like that. We know how to solve that. Okay, subtract 1, divide by 3. When solving exponential equations, we need to use logarithms. You will not be tested over logarithms, so the only tool we have to solve is to graph both sides of the equation. Okay, you may be able to do a couple of these just with some scratch work, which you will. You probably have a couple exponential equations. Okay, this is where having a graphing calculator would be nice. It makes it a lot simpler. Okay, so it says solve the following exponential equation. So we're just going to graph both sides of the equation and find the intersection point. Okay, so first of all, we need to go ahead and turn our Scatterplot off. Okay, so turn this off. Window, let's go ahead and actually let's graph first and then we'll change the window. Okay, so our first one is 7 times 3 to the x, okay? And then our second graph is 216. Okay, this 7 times 3 to the x, okay, I'm just going to go ahead and do a quick picture since we didn't graph any exponential equations or exponential functions. This is growth. Okay, so you have c equals 7, a equals 3. Okay, that means this is growth. Okay, so the picture looks like this. Exponential growth always looks like this. You have an asymptote here, and this point is 0, 7, or 0c. Okay, so we should have that picture. Okay, when we graph 216, that's a constant function. Okay, so we're going to have a horizontal line. So we can graph this by hand, but this is the point we're looking for. Okay, which I definitely suggest having a calculator for that. Okay, so we at least need to go up to 216 to get in this line. Okay, so let's change our window. I'm going to do -10 to 10 for the x. For the y, I'm going to do -10. Let's go up to 250. Okay, just so we can have a good picture. Okay, so here's our exponential equation, or the equation, or the, formula on the left. So there's 7 times 3 to the x, which is exactly what we thought it would look like. And then here's 216. Okay, so we just need to find the intersection point. So that would be second trace, calculate, down to intersect. Okay, first curve, second curve, and then guess that point. It gives us x is about 3.12. So I'm going to go ahead and write out this point was 3.12216. Okay, so the solution would be about 3.12, so approximately. Okay, number 2, we want to do 5 times 1/6 to the x equals 0.5. Okay, so again, we know how to graph this. This is an exponential function. C equals 5, A is 1/6. Okay, that's less than 1, so we know this is going to be decay, so it's going to be a little different picture. It's going to look something like this. Okay, where this point is 0c, so 0.5. Okay, 0.5 is going to be somewhere down here, so lower than 5. Okay, so we want to, it's going to hit somewhere here. We want to know what this is. Okay, so let's go ahead and graph with our calculator. I'm going to change the window also. It was 5 times 1/6 to the x, and then this was 0.5 or 1 point, yeah, 0.5. Okay, window, let's just do standard. I think that would be plenty. Okay. So there's our first function. It hasn't started yet. There's exponential decay, which is exactly what we thought it would look like here. And then 0.5 is going to be a horizontal line. Okay, and you guys can see it hits about here. So we're trying to find that point. So second trace, go down to intersect. First curve, second curve, guess. X equals, it looks like about 1.29 and 0.5. So this is 1.29 and then 0.5. Okay, so X is about 1.29. Okay, so this is probably the simplest way to solve exponential equations. Again, you have to use logarithms, which are not going to be tested over. Okay, they might give you a couple that you could do in your head or just simple scratch paper, but this is probably the easiest, most accurate way. Okay, and that ends exponential functions. So next we're going to start quadratic functions. We'll go ahead and stop there, and then we will pick back up at quadratic functions.